All right, guys, we're going to talk about polar coordinates and graphing today. I'm trying a new system for this video, so you can see it's a different background color. I'm really too excited about this. This is what my life is like right now. Let me know if you like it or not, or if you like the black background with the green writing better. You should tell me. We're going to try this out. I'm not sure what, I've been trying to research like what colors are best. I can't really find anything yet. So we're going to do a new graphing system. So we are used to the Cartesian coordinate system, right? That takes basically a two-dimensional space and it breaks it up into basically a grid, right? And we talk about the origin, and we speak about where we are. If I grab a point, we talk about what its distance is from the origin. So we're going to talk about something a little bit different today. We're going to talk about how could I actually think about a point still in a two-dimensional plane, but instead of looking at horizontal and vertical distance, now we have this exciting idea of angles, right? And maybe distance from the origin, including an angle through what we go through. So here's what a polar coordinate basically is. So the whole motivation behind this is if I took a graph, or if I took a point, right, anywhere. So without loss of generality, I'm going to put it in second quadrant, or that's the first quadrant. And basically, yeah, I could talk about the horizontal distance, right, and the vertical distance, but I could also talk about its direct distance from the origin, right? And if I were to take that distance right there, right, that R, we'll call it, distance from the origin, and I could actually look at what is the angle that I would have to go through, right, to take that ray basically and get up to that point. So that's exactly what polar coordinate is. So there are two things that define basically where this point is in the Cartesian coordinate system. Those two things that are defined that define that point basically is R, which is going to be the distance the point is from the origin, that straight distance, not the horizontal distance, not the vertical distance, but the actual distance from the origin. That's not how you spell origin. Sound it out, Sarah. Origin. So that's the distance from the origin. Okay, and then the theta is going to be the angle that you go through, okay, to get to that point. So this is the theta, that's the angle. So when we look at polar coordinates, we can be in degrees or radians, okay. A couple of things. I said the origin, a lot of times we'll call this the pole, okay, so that would be the pole here, or the origin, doesn't really matter. The x-axis is what we call the polar axis because our angle is always going to be measured from the polar axis. You just like before when we talk about angles, we never actually measure that angle from the y-axis, right? All of our angles are always measured from the x-axis, okay? So this point right here in a Cartesian coordinate system would be the point xy, but in our new polar, exciting polar coordinates, we're actually going to state the r first, that's the distance from the pole, and then the angle, okay? Excuse me. So again, r is the distance from the pole, and theta is the angle. I hope that kind of makes sense. Now we're just going to do a bunch of examples on this. So if I were to ask you to graph a point that's in a polar coordinate, right, what I'm going to give you is I'm going to give you an r, I'm going to give you a theta, and then we have to figure out where that's going to be. So here's how I'm going to give you an actual a graph that will be a little bit better, but let's talk about, oh, sorry about that. Isn't that cool? I can just like move the screen up. So that's gonna be pretty neat. Anyway, so like for example, if I had the point 1, 45 degrees, okay? So what ends up happening when we're dealing, no, that's not what I wanted. When we're dealing with polar coordinates is we're looking at these distances. Look at it, guys. I have, actually have a ruler with this. This is so exciting, and it'll tell me 90 degrees. So look at that. Isn't that amazing? I'm amazed by this. Probably everyone knows about this except me, but I think it's pretty awesome. Okay, look at my lines. They're actual lines now, which is super exciting. All right, so if I look at, I want to be a distance of 1 away from the pole. This is all going to depend on your units, right? Are we 1 centimeter, 1 meter? But if I just look at a regular Cartesian coordinate system, and I'm going to introduce my own units maybe. So I have something like this. So let's just graph a couple of these, and then I'll show you that this kind of, how this generates the polar graph that we're actually going to look at. So 145 degrees, I want to be 1 away from the pole. So it's not 1 in the x direction or the y direction. That's what's a little bit tough about this. But if I'm actually 1 away from the pole, I'm going to be on this, let me undo that really quick. I'm going to be on, oh, look at, I just messed up my perfectly straight line. If I'm 1 away from the pole or from the origin, basically I'm going to be any point, right, along this blue, beautiful, pretend it's a circle, blue circle, and then I'm going to be at 45 degrees. So when I show you what a system, or when I show you what the graph, basically graph paper for a polar coordinate system is, it's just going to be a bunch of circles actually, because if you notice, if I'm 1 away from the pole, I could be any point on this circle, right? That's a distance of 1 away from the pole, but I want to be 45 degrees. So I know 45 degrees is this angle right here. So what is my actual solution, or what is that point right there? It would be this point right here, right? That is 1 away from the pole and is on a 45-degree angle. Isn't that cool? So like if I wanted to look at the point 345 degrees, right? I would go to a circle that is 3 away. Pretend this is a circle. This is my circle. All of these points right here. Oh, guys, this isn't a horrible circle. All of these points right here are 3 away from the origin. But if I want to look at being 40 on the 45-degree angle, it would be right here. So this would be 1, 45 degrees, and this would be 3, 45 degrees. Okay. So you might ask yourself, I have negative numbers, correct, in my Cartesian coordinate system. And right now I'm only getting points that are in the first quadrant. Now I could mess with that, right? If I made this like 135 degrees or 225 degrees. But here's what happens if we have a negative. So, and we'll write this all down, okay? But what if I asked you to plot a negative 145 degrees? So what a negative is going to indicate to us when we have an r that is negative is we want to go in the opposite direction. So if I have, I'm going to first actually look at the angle here. So 45 degrees, if I just, there's my 45 degrees. What that -1 means is if I were to extend this line right here that indicated the 45-degree angle, I just want to go in the opposite direction. That's what that -1 means. This says in the opposite direction on the 45-degree angle line, right? Or that ray, if I could extend it. Okay, so I want to go in the opposite direction. I'm still going to stay on this circle of radius 1. And so what would this point be right here? This point would be a -145 degrees. I hope that kind of makes sense. Negative angles, we would plot a negative angle just like we know how to plot a negative angle, right? A -345 degrees would be out here, right? Because it'd be on the 45-degree line, but it'd just be in the opposite direction. So let's just graph a bunch of these. That's really what I just want to do, and we'll do what I want to do because it's my video. I'm kind of kidding, but we really are. I mean, whether you listen or not, I can't control that. So let's plot the given polar coordinates. Or just let's plot the given points, and let's get a polar system kind of up here that'll be a little bit more easy to use. Okay, so this is what a polar graph looks like. Notice all the different circles. There aren't any units to these circles, so we'll just assume, you know, the first circle is 1 away, the second circle is 2 units away from the pole. You notice it has all of our degrees on there, and we're ready to plot some points. So I'm just gonna write down a bunch of points, and then let's talk about how we're gonna plot them. So let me just write down these points. And we can do radians, we could do degrees, right? Of course, I'm gonna do both, but I just wanna put all these points down, and then we'll look at plotting them. I have a bunch. I'm almost done, I promise. And then let's look at 5. Okay, so let's look at all of these points and how we're going to plot them. We'll do some colors. Guys, this new thing has some really cool colors. I'm really excited about it. All right, so let's look at 3 60 degrees. So first, I'm going to look at, here's my 60 degrees, right? And then I want to be 3 away from the pole. So I just go up 3, 1, 2, 3. So there I am. That's going to be my 3 60 degrees. I am 3 away from the pole along the 60 degrees. Pretty easy, right? Sometimes these can get a little more complicated, but we're not worried because we've dealt with these angles so much before that we don't really have to worry about. 0, 10 degrees. So 10 degrees, right? Here's my 15 degrees. 10 degrees is just going to be about, what, 2/3 of the way up there. But look at you guys, it says it's 0, right? So I want to be 0 from the origin. So actually that point is just going to be right there on the pole, or the origin, because I want 0 away. So the interesting thing about these points is they're not unique. So what I mean by they're not unique, in the Cartesian coordinate system, you know, this point would just have one representation. I would go over 2 and up 7 or something like that, right? But in this case, if I look at 360, that could be 360, or I could go the opposite direction and I could get 3 negative 300, or I could actually be at negative 3 240, right? Because I could be the opposite way. So with these points, realize that there are a lot of different ways we can express these points. Let's look at another one. So negative 5, 120. So the first thing I'm going to do is, I know that negative means I'm going to go the opposite direction. So let's find 120 first. So here's 120 degrees. And then if I continue on this line right here, which it's a little bit hard to see, but that's 60 degrees away, right? So I'm going to be right here along the 300 line, and I want to be 5 away. 1, 2, 3, 4, 5. So this point right here is the negative 5, 120. So again, I'm on the 120 line, and instead of going up that line, I'm going to actually go back, and there's my negative 5, 120. That point could also have been represented by 5, 300, right? If I just wanted to be on the 300 line and go 5. Okay, aren't these fun? I think they're a good time. That probably doesn't surprise you that I think that that's true. All right, 1, negative 60. So negative 60 degrees. So this guy right here, I won't be putting these, I'll put the lines, but I probably won't be putting the actual labels. You'll need to know those. But if I look at 1, negative 60, so I'm going to go negative 60 degrees, which means I'm going to go 60 degrees in the opposite direction, right? So negative 6, this guy right here is coterminal with a negative 60 degrees, and then I want to be 1 away. So there's my point right there for being 1 away. Okay. Oh, let's keep going. This is a good time. What about 3 pi over 2? 3 pi over 2 I know is the same as 270 degrees. So I'm going to be along this 270 degree line, but I'm going to be 2 away. So there's my 3 pi over 2. Let's look at another one. Maybe I'll use a color I actually haven't used yet. That would be exciting. Negative 4 pi over 3. So the negative 4 tells me go in the opposite direction, but I want to be at pi over 3. So here's pi over 3. Pi over 3 is the same as 60 degrees. So I'm going to go along this line right here, right? This is the line that is 60 degrees. And then I'm just going to go in that opposite direction. Let me get rid of that really quick. So that opposite direction is 240. How far away do I want to be? I want to be 4. 1, 2, 3, 4 units away. And so there's my point there. All right, a couple more, and then I think we got them. Oh guys, you need to see this. You need to see this color right here. Look at this. Whoa, isn't that awesome? I know, I'm just going to color that for you. My daughters are going to go nuts when I show that to them. Let's use that one for this guy. So a negative 5, negative pi over 4. Okay, negative pi over 4. We're 45 degrees right away. So this is coterminal with, oh, look at that, a negative 45 degrees. And now, okay, so let's think about this. So the negative 45 degrees is going to be this line right here, right? That negative 45 degrees. But I want a negative 5. So I don't want to go in this direction of that negative 45. I want to go in this direction. So I'll be 1, 2, 3, 4, 5. So there's my negative 5 negative pi over 4. Okay. I hope that makes sense. Those can be a little tricky. If you get stuck on those, just let me know. I think I messed up that guy right there. There we go. All right, and then finally, let's do another rainbow color because they're just too much fun. Look at that one. Isn't that neat? It's still kind of rainbow, but all right. And then 5 11 pi over 4. So let's think about where 11 pi over 4 is. So if I think about this in radians, this is 0 pi over 4. This would be 4. Oh, I don't think we better use that. This would be, we'll do pink. This would be 4 pi over 4, right? Also known as pi. This would be 8 pi over 4, also known as 2 pi. And so 8 pi over 4 to 11 pi over 4 is going to be 3 pi over 4. So 3 pi over 4 is pi over 4 away. So we're actually on this line right here. Okay, and I want to be 5 away, so look at that, I'm on the same point right here. So these points actually are exactly the same, they just look different, right? So we found that it's not unique. Those points are the same, they just look a little bit different. I hope this makes sense. Let's kind of summarize how we're going to do this, how to plot these points. So to plot in polar coordinates, so to plot polar coordinates, let's talk about this really quick. Maybe we should have done this before, but let's go ahead and write this down. So first step, you want to locate. So you want to locate the angle theta first. The reason you want to do that first is because then we know if we're going to go forward or backward depending on what r is. So the second step then, if r is greater than 0, right, you move along that ray. And we could call that, you know, if you look at, if this is my origin O, and let's say this is my point P, then we move along the ray OP, okay? If R is negative, okay, then we move in opposite direction. Of OP. So if this is my ray OP, right, if R is negative, then we're going to go in the opposite direction of OP. Okay? Good. I think that's about it. That's pretty easy, I think. Now I bet you're asking, but Sarah, wouldn't it be nice if I could take these Cartesian coordinate systems that are now quite boring to me, because now I know what polar coordinates are like. Wouldn't it be nice if I could actually change from Cartesian to polar? And I'll tell you, yes, that would be very nice. And let's go ahead and do it. Okay. Oh, I'm running out of whiteboard. That's all right. I'm kind of learning how this works. This is pretty great though. I'm really excited about it. So let's look at converting, converting from rectangular coordinates to polar coordinates, or maybe even converting like equations to polar. So let's look at converting to polar. So if you are given, and you're going to see this is not that hard. We've actually kind of already done this. We've talked about this a little bit when we've talked about the trig form for a complex number. It's kind of the same idea. But if I want to convert to polar, let's think about this a little bit. This actually isn't going to be too hard. It's everything we already know about this stuff. So without loss of generality, let's put a point. And let's give it the Cartesian coordinate system, or the regular coordinates, right? If that is x, y, let's look at how I can find the relationship between it and my polar. So remember, my polar is going to care about, what is the polar coordinate going to care about? It wants to know the distance from the origin, and it wants to know the angle theta. So this is stuff we've actually already seen. So converting to polar, we have some relationships that we're going to see, and we are going to know this already, you guys. So we know, right, that this distance here is x, this distance here is y, by definition of what a Cartesian coordinate is. And so what do we know the relationship is? Well, how would I find r? Well, we know that r squared, well, let's write this way. X squared plus y squared is r squared, right? Or another way of saying that is that r is going to equal the square root of x squared plus y squared, right? And in general, we'll take the positive of that. You could write a polar coordinate. Remember, these aren't unique, so you could take the negative of that, and we could just determine what we want to do. But in general, what we want is we want to be kind of consistent with how we pick r. We usually, if we're going to go ahead and go From this, we usually take the positive r, but you don't have to. You don't have to. And then what are my other relationships that we have here? Well, if I look at the cosine of theta, right, the cosine of theta in this case is going to be x over r, or another way of saying that is x is equal to r cosine theta. This should look very familiar, as we used this when we talked about the complex form of a trig. The trig form of a complex number. Sine, of course, is y over r. We remember back at the beginning of this class when we first introduced those, and now they're like our children that we've watched growing up. I don't know, that might be pushing it a little bit. And then the tangent of theta, which this is going to be kind of, sometimes you use a tangent, sometimes you don't. I think it's pretty easy to use the tangent, although you have to find r anyway. But we know then that the tangent of theta is equal to y over x. So these are relationships that you're going to need to know. You're going to need to know the relationship between polar coordinates and rectangular coordinates, that x is our cosine theta, y is our sine theta. If you're in doubt on a test or something, why don't you draw your little triangle and start making the relationships between these variables that we have. So let's look at a few examples. So let's convert. Oh, look, I didn't run out of room. Look at that. Well, we kind of need that though. Let's remind ourselves about that. So let's convert to polar coordinates. And again, these aren't going to be unique. Unless the problem tells you, make sure r is positive, make sure theta is the smallest positive angle between 0 and 2 pi. Really, you can pick whatever you want, really. So let's do, how about a -4, comma 4. Okay. So what I usually do on all of these is I draw the graph. I mean, it's fine to memorize some of this stuff, but I also like to draw the graph and just kind of see what is happening. So I know I'm at -4, and I'm up at +4 in the y direction. So this is the point that I want to find the polar coordinate of. So remember the polar coordinate, right? What do we need? We need r and we need theta. So here's my theta and I need my r. So again, how do I find r? Well, r is just going to be the square root of -4 quantity squared plus 4 squared, right? So I get 16 plus 16, which is the square root of 32. 32 is 16 times 2, so that's going to be 4 root 2. Okay, so right away I know that this coordinate right here, if I'm ready, I can actually write half of my polar coordinate. I know I'm going to have 4 root 2 as the r. Now I just need to find the theta. And this is where I like to use the tangent, just like we did with the complex numbers. You, of course, could use these because we know what r is. But if we just look at the tangent of theta, I need to find a theta such that its tangent is y, which is 4, over x, which is -4. So that's -1. So I need to find an angle in the second quadrant, right, whose tangent is -1. Well, I know my reference angle must be pi over 4, or 45 degrees. I guess I should tell you if we should use degrees or radians. Let's do both. So I know my reference angle is 45 degrees, so I want an angle in the second quadrant that has reference angle 45. So I'm going to set theta equal to 135 degrees. So the polar coordinate for this, a polar coordinate, a representation in polar coordinates of this point, one is 4 root 2, comma 135. What are some other ones that I could have done? Well, I could have done 4 root 2 and then a -225 degrees, right? If you think about that, what is this angle right here? That's 180 plus 45, so that's a -225 degrees. Or we could do in radians, right? 4 root 2, 3 pi over 4. We could do 4 root 2, what would that be? A -5 pi over 4? 1 pi over 4 away from that. Or look at this, you could even, if you wanted to get a little crazy, right, if we extended this line right here, this is a -45 degrees, and then if I go in the opposite direction, I could even say this is a -4 root 2, comma, -45 degrees. There's an infinite number of ways that you could do this, you guys. I could also have said and negative 4 root 2 comma 315 degrees, right? That would give me the same point. All of those would give me that same point right there. So this should look pretty familiar because it's very, very similar to what we did with the complex numbers, right? Similar to it. Not exact, I understand that, but pretty similar. And let's do one that maybe is a little bit harder. So what about this? Negative 3/2, comma, negative 3 root 3 over 2. So I'm gonna graph this really quick. Negative 3/2, negative root 3 over 2, that's gonna be a little bit more than that. So maybe right about here. And again, what do I want? If I want I want an r and then I want a theta. And I believe your book asks you to find it in degrees and radians and use the smallest possible positive angle. So basically an angle between 0 and 2 pi, right? So I'll try and be kind of clear about that when we get there. So let's see what we got. Let's figure this out. So what do I have? I know that r is equal to the square root of a negative 3/2 quantity squared plus a negative 3 root 3 over 2 quantity squared. So let's see what this gives us. So this gives us the square root of 9/4. Here I'm going to get 9 times 3, right, which is 27/4. Oh, this is pretty nice. So I get the square root of 36 over the square root of 4. So, well, I could have done also 36 divided by 4 is 9. Oh my goodness. I can't believe I did that, but I did. Hey, there's more than one way to get around it. So what do I know r is? I know r is 3. And let's figure out the rest. So again, tangent of theta, I want a theta. And if you don't like dealing with tangent, you can always use like cosine or sine, that's fine. Tangent is going to be a negative 3 root 3 over 2 all over negative 3 over 2. Flip it good, and multiply. Right, so we get nice things happening, and those are positive. Tangent should be positive in the third quadrant. So I need an angle in the third quadrant whose tangent is root 3. So what's my reference angle, right? The tangent of 60 degrees, I believe, is going to be my reference angle, and I want to be in the third quadrant. So what do I want here? I want this right here, and so that's 240 degrees. So if it's asking for the smallest positive number, right, between 0 and 2 pi, then the 240 degrees is it. Also in radians, that's 3. Remember, 60 degrees is pi over 3, so this would be 3 pi over 3. So I want one more pi over 3, so that's 4 pi over 3. And those are my solutions. And again, I have an infinite number of solutions to that. If I wanted to keep going, I sure could. Oh man, we're almost at 30 minutes already. So I'm going to, I'm going to stop that there, because the next part of this is talking about how to actually take, oh, actually, no, we're not going to stop there. Let's do one other direction. Sorry. Let's do one other direction. What if we wanted to change from polar to rectangular, right? So let's do that, and then we'll stop and we'll do a second part of this lecture. So let's convert to rectangular coordinates. What if we were given, let's say we are given an angle in polar coordinates. Let's figure out what is the corresponding angle in rectangular coordinates. Not corresponding, what's the same angle, right, in rectangular. Let's start off kind of easy. 630 degrees. So if you think about this, 630 degrees, right? Here's 30 degrees and we're out 6 away. 1, 2, 3, 4, 5, 6. So like 6 circles away. So I should be in the first quadrant. Now remember what our relationships are, right? We know x squared plus y squared equals r squared. What else do we know? We know x is r cosine theta. We know y is r, s is r sine theta, and we know that tangent of theta is equal to y over x. So this tangent of theta equals y over x, this is really only used to find theta. I mean, you could use it for other things also, but when you are converting from polar to rectangular, these are the guys that you want to use, okay? We know what r is. This equation is not really going to help me find x and y necessarily, but the x equals r sine theta and the y equals r, x equals r cosine theta, y equals r sine theta. Those are the guys, right? Because if I want to find rectangular, what am I looking for? I'm looking for an x value and a y value. Okay, so what's nice about converting to rectangular is you literally, I'm using that in the correct sense here, plug it in. So I'm going to do cosine of 6, right? That's my r, that's my theta. 6 times the cosine of 30 degrees, so that's 6 times root 3 over 2. Get out of the way, tangent. So what do we got? X is 3 root 3. And then for y, we have 6 times the sine of 30 degrees. So that's 6 times 1/2, which is 3. So your final answer, this is not your final answer. What is your final answer? It's written as a point, 3 root 3, comma 3. That's your final answer when converting to rectangular. All right, one more, and then this will be part 1 of the lecture, and we'll finish up this lecture another time. So what about, I like this one because it's kind of interesting. How about 1/7 pi over 4? Okay. Actually, I might do one more after this. So x again this is your r, this is your theta, is going to be 1 times the cosine of 7 pi over 4. So let's think about where 7 pi over 4 is. It's not quite 8 pi over 4 is 2 pi. Reference angle is pi over 4. Cosine is positive in the 4th quadrant, and I know that the cosine of pi over 4 is root 2 over 2. So x is root 2 over 2. Y is 1 times the sine of 7 pi over 4, right? And because we're in the 4th quadrant, sine must be negative. So I have 1 times a negative root 2 over 2, which is just a negative root 2 over 2. So what's my solution for this one? Root 2 over 2, or 1 over root 2. You don't have to rationalize it for me, but you have to find my math lab, so you might as well just do it. So we get root 2 over 2, negative root 2 over 2. Does that make sense? Well, if I were to graph this point right here, right, 7 pi over 4, I'm going to locate the angle, and then I'm only 1 away, so I'd be right here. Yeah, that makes sense, right, because this is going to be in the 4th quadrant with the same x and y. All right, and then the last one, what if we had a negative 3 pi over 2? Now this one we actually, if you don't want to use the formulas, you could just think about this one. And I know that's asking a lot, but you could just think about this one. So 3 pi over 2, right, we're looking at this angle right here, but because it's a negative 3, we're going to go in the opposite direction, and we're going to go 3 from the pole. We're on a y-axis, so I would just go up 3, and so I should be right here. So I can easily convert that to rectangular, because what should that be? That should be 0, 3 in rectangular. Now, let's make sure that that actually is true. Does that satisfy x equals r times the cosine of the angle? Well, cosine of 3 pi over 2 is 0, so sure enough, that's 0. And then finally, whoa, and then whoa. And then finally, y is a negative 3 times the sine of 3 pi over 2. I hope this is going to work. It sure does. Sine of 3 pi over 2 is a negative 1. So we get 3, and all is wonderful in perfect math world. All right, you guys, that's really fun. I like this new system. I hope you like it. It looks really cool how much work we've done. If you have any feedback on it, please let me know. And stay tuned for part 2 of polar coordinates. What we're going to look at in the next part is how do I take an equation that's in rectangular coordinates and switch it to polar, or vice versa.